concepts of non-equilibrium statistical mechanics, having in particular, but not exclusively, in mind application in geophysical fluid dynamics, and present results that are mostly been obtained with Frank Lunkheit, Francesco Ragone, and Stefania Sarno, and some very recent ones as well. So let's so we have in the geophysical fluid dynamics clearly, as we have already seen, problems, gross sometimes not so gross, problems in our models, and we have discussed that there are various conceptual and in fact also epistemological issues in treating the relationship between models and system. And I will concentrate in the concept of response and how we can use response to approach a variety of problems. Already Jeroen Wouters has discussed how response can be used in a sort of a slightly convoluted way to construct a parameterization, response as a coupling with some other degrees of freedoms, and we'll try to present some problems. And I would like first to give a brief overview of how we can use response to study the impact of deterministic and stochastic perturbation, and I will present 3 points of views. One is doing a spectroscopy of our system. One is using noise as probe, and the last one is using a broadband forcing. And so actually the first and last correspond to very clear experimental practices in optics as spectroscopy per se, and something like synchrotron radiation. And we can use these ideas. And then I will try to convince you that we can use these ideas, in fact, to predict climate change with some predictive power. So let's see, going back to the first and then to the last point. So this is, I'm here referring to the IPCC scenarios. So these are scenarios proposed to study future climate change. This is the fourth assessment report. And as we see, we have, these are possible scenarios of CO2 concentrations, and this is what is used by the international modeling community to study, as a, let's say, mainstream investigation of climate change. And this is a very important thing. And as if we look at what models report, this is the on taking the most typical observable of climate change, that is changes in the global surface temperature. Well, this is what we obtain depending on the various scenarios, and we have a band which refers to the so-called model uncertainties, which is in fact is reflected more precisely in the bigger band on the right-hand side. So what we get here is the so-called average ensemble model average that has been already discussed a few times, and this is the entire range we get. And again, I want to stress how broad, how large is this range, and those here who have experience of many years in climate modeling know that this has not decreased a lot, if at all, in the last 20 years. So my problem is, do we need to do all these simulations? And I think the answer is not necessary. So this is how I'm going to end. I'm learning now a new way of presenting. You put a picture at the beginning and then you go there. I think it's a great idea. So this is one of the last figures you will see. So the black is the result of let's say, a climate change experiment performed with a very reasonable climate model, not of the IPCC class, but let's say of the IPCC class as it were 15 years ago. And the blue is the prediction we get. Okay? So we will describe this. And the scenario is a classical, one of those scenarios. Classical scenario, 1% increase of CO2 per year. So this is a very somehow classical, realistic, practical problem. Now, let's make few steps backwards and try to connect with various things also discussed here. So when we talk about response theory, and we have seen this appears in many different fields, we are basically, it's a very conceptual thing. It's, apart from the technical aspect, which can be extremely difficult and also difficult, it is an experiment where we have a system, a measuring device, a clock, and a turnable knob. There's been already some discussion of knobs. That's exactly what we do. what we do, we change the knob with a certain time protocol when we measure our system at a given time. And we plot out the data, we repeat, and we try to get outputs here. And we construct a response theory if we can predict these changes looking at the properties of the unperturbed system. And then we can start to put some concept on the table. Well, if I have a divergence in the response, maybe this is related to what, now it's called a tipping point, some catastrophe in my system. And somehow this to me is an attractive environment to study climate change, because what we face, in fact, is still in the literature, it's very unclear what is climate sensitivity, what is climate response. If not, there are some ad hoc definitions. And we use a lot of these experiments, and sometimes we don't know to do, and we just average things, which is like really losing a lot of information. Now, we have to, if we want to construct a theory, we have to put it in a setting, and the setting can be more or less useful or more or less easy to process. So let's start from the last point here. Let's say that we expect, as a physicist, I expect that response theory as a concept sounds extremely good, and expect it to work in very general cases. That's the first point. Then again, we have to prove things, and this is another kind of activity thing. So I think we can do two steps. So what has been done has been to construct the theory rigorously for a class of dynamical system, and then we can write the theory. Then we have to interpret the connection between mathematics and physics. So I think it's very important to say, okay, we can construct the theory rigorously on axiom A system, but of course nature is not axiom A, I would say fortunately, but on the other side, axiom A is a good model to look at nature, so it's a good macroscope, not a microscope, it's a macroscope. So I think the idea of Galavotti-Cohen is crucial, because it exactly entrusts us to use a mathematical model to look at high-dimensional systems. So again, of course we have to do assumption, but there are always assumptions. So this is, I think, a good point of view. And again, clearly, response surely will apply outside axiom A, at least for finite time, at least with finite precision. So the response theory allows us to go from an unperturbed system of this form, add some perturbation. It's been already presented, I think, 3 or 4 times, and I will I will just say that we write the expectation value of any observable as a series where we can construct the perturbative term using the convolution, multiple convolution of a time modulation of a Green function. And of course, here we are just rewriting, and all the dynamics is in here. And this is the difficult beast. I will emphasize that the Green function comes from a suitable composition of unperturbed projection forward in time and impact of perturbation on the unperturbed state. So that's why it's a response theory. There is the unperturbed state here, and there is causality. So things happen after a kick has been given to the system, and this is I think a very important aspect, because this is the basis of all the formal properties we can use in all generality. So once we have this, we are out of physics, in the sense that many physical systems will obey this. And so if we look at the linear case, we have a very simple structure. So the response will depend by a Green function, which depends on the observable we consider and on the forcing. So it's in some sense, it's a phenomenological theory. It's a very theoretical setting, but it's a very phenomenological point of view. And then we have a convolution. Now, if we go from time to frequency, we construct from Green function a susceptibility. So in the world of events, of phenomena, where frequencies were more relevant, it's good to use this. If we look at time, if we like time, we will look at Green function. And of course, there are problems of convergence, but that's not the goal here. So now, a problem is, it's been discussed quite a lot in the literature, is can we And I mean, this is closely related, in fact, to the fluctuation dissipation theorem. It's a slightly not obvious way to go there. But if we look at this green function and we assume regularity for the measure, we can do an integration by part and we get this form. So this form of the green function sees the correlation between the observable at time t and another property that Matteo Colangeli called the dissipative flux. And so if we know that if the measure is singular, we just cannot do this operation. So we are blind. It's really bad. On the other side, we have a lot of experiments. I mean, at least many experiments in a simple or not so simple models of atmospheric dynamics, where actually, if you use this thing, and actually in a simpler setting, we have a good approximation. And the question is why. So the result is wrong, but it gives a reasonable result. We have to see where the problem is. I mean, first, one has to appreciate that if one considers coarse-grained quantities, you have to expect that a form of this form will work. You can construct it, and that's one of, as an example, one of the products of the work that Wouters has presented is this. And it's also clear that the choice of the observable is crucial because it will be related to how fine is the grain of the structure we look at. Now, this is something to go from the function, from the form of this fluctuation dissipation theorem I showed, which is this, to what we find in most textbooks. So this is very important. I found it to go through these steps very useful. So in order to get to the correlation, so people say, okay, the fluctuation dissipation theorem relates the response to correlation. There are various steps in between that are not trivial. First, the forcing has to be along a direction and constant. Second, the observable has to be one of the variables of interest. And third, the distribution has to be Gaussian. And then we get to this. So depending, if we use this, there are various levels of approximation. And we don't know whether all of them are good. Now, an important aspect, if we look at frequency domain, is that the Fourier transform of the green function, the susceptibility, obeys integral relations that are useful to reconstruct the response. If we look at frequency dependent forcing, but in a second we will see why this function is useful to determine limits to prediction. Okay, let's first okay, if we use the theory on a very bad system, worst system, which is Lorentz 63, in fact, you can do the spectroscopy of the system, and you can construct resonances and dispersive structure like in an atom. In fact, it looks very much like that. And you know, I never really understood very well what was this resonance, except when, of course, you have a resonance with the jump of the two sides of the butterflies, and then talking actually with Eckert, I realized this has to do with unstable periodic orbit in this. So you get a resonance if you get if you have a resonance with an unstable periodic orbit, and you can rephrase the problem in that language from scratch, which is quite.
You have a lot of unstable.
Yeah, but this is the dominant. This is the dominant one that dominates by far this. If you choose other observable, you start to see others. In fact, now. So this is the spectroscopic point of view. If instead of forcing the system with the cosine I indicated before, you force it with noise, you get something different. And in particular, you can expand the SRB measure and see that the correction to any observable is proportional to the intensity of the noise. So you get a correction. This is useful, and it gets more useful because if you go into Fourier space and look at correlations, you find this general result that we are also using for more interesting system. That is, the difference between the power spectrum of a stochastically forced system and of an unperturbed system has to do with the square modulus of the susceptibility. So to the response you get from a periodic forcing. So noise informs us by mixing phases on the response at all frequencies. So noise is an extremely good probe And so we have another way, again, to look at the frequency-dependent response. Now, let's present an example. It's a very simple model. It's the Lorentz 96 model. So it's an extensive model with intensive property which represent metaphorically the dynamics on a latitudinal belt having advection, dissipation, and forcing. And it has F is a parameter of forcing. We put ourselves in the region where we are in a chaotic regime, and we put just a simple forcing, a simple perturbation. We increase the forcing. So, as an example, you can construct the do the spectroscopic analysis, and you get, again, resonances, and you can study multi-body, many-body or single-body effects. And if you look at the use stochastic methods, you can actually be able to get the asymptotic behavior with much higher precision and much more efficiency, which is quite encouraging. Now, let's use the formal properties and forget about the chaos of the system. This is my response. Let's say I force the system with a certain protocol T. I measure this, I invert, and I can derive the susceptibility. So I can do inverse Fourier transform. I get the Green function, and with this I can do predictions. So now I can go into the range of predictions in the linear approximation, but you can do this in nonlinear term as well. So as an example, after a colleague actually who was here in Cambridge a long time, Fenwick Cooper, told me, yes, but you can construct all the linear properties you want, but if they are not able to give you prediction, this is totally worthless. And he was right. So what we did was trying to reconstruct again with the broadband forcing the Green function and to have prediction. So we reconstructed the Green function with a simple kick, a step forcing, and try to predict the impact of a sinusoidal perturbation. So this is a very small set of experiments. I've been able to construct the Green function, and look that we are working with a time scale of 1, and it works extremely well. So this is very encouraging. There is a problem. If you look at the output, you're going to have noise. You're going to have noise due to two effects. You have a finite number of ensemble members, finite length of your integration, and this will constrain the signal to noise ratio in what you measure. You can, looking at the asymptotic behavior of the susceptibility and of your forcing function you choose at the beginning, you can construct, that starts to become interesting, that you have a time scale below which you are blind, and you have a scaling property. This tells you, if I'm rich and I have the possibility of doing more runs and longer runs, I can move move my time scale of predictability to smaller and smaller scale. So I can predict not climate change in 100 years, but in 10 years, or in 1 year, or in 1 season. Okay? So here is a scaling we get. So there is nothing special about the time scale, except that we need the time, we need the data to resolve noise from signal. And you get this looking at the susceptibility. Now, let's play with climate. So if I want to give a measure, an image of the differentiability of the measure, this is a snow-free snowball system with transitions, very terrible bifurcations taking place here, but in each of these manifold things are extremely smooth. So we can hope to do climate change here and use this is very smooth to try to think of using response theory. So now let's do a climate change experiment. So it's the same slide as before. I have just changed a few words, and it will look the same. So we look at surface temperature as observable. We force with an increase, a step increase of CO2, and we run many simulations, 200, so it's not so many simulations. We try to reconstruct the green function. It's just the derivative in time of this thing, and then we will try to predict things using a different pattern of forcing. So if we predict, we have won. Okay? Because this means it's enough to do one set of climate change experiment to reconstruct many different ones. So now we have to. That's a wonderful. It comes from previous from Klaus Friedrich. It's actually a very nice concept. So if we want to use theoretically some slightly sophisticated tools, we need flexibility in the modeling. And as people who do climate modeling knows, the biggest model is not the best model for every problem. Okay? So what we're using here, it is actually a climate model with everything: atmosphere, vegetation, even ocean, sea ice thermodynamics, and which is an open source and model that is being used in many countries now, in fact, because it's open source, and which gives you a lot of outputs, has a nice graphical user interface, and we are bringing this to many countries in Asia as well. This is a good model that runs fast and is good enough for our purposes. So now we do the experiment. So this is this increase in 1 point of the CO2 up from 360 ppm to 720. And this is the ensemble average value of the temperature. And this is 1% increase. Look at the black line. The red line is the T at 500 millibar, and the magenta the same. So we have a change in the temperature at two levels, surface and 5 kilometers basically. So this is the ensemble average. So now the goal is, knowing this, I want to predict the black. So I repeat the same I've done before, no change, and this is the result. Okay? And this is, you can find the formal description of what is climate sensitivity, which is the real part of the response at frequency 0, with the observation of the at all frequencies. So this is the connection between climate sensitivity and the response at all frequencies. So this is a formal relation. And now, let's look at more delicate things. Vertical stratification. So that is what we have seen before is a change of a lot of degrees. Let's look at the changes. See in surface temperature minus T500. So this is the observation, and this is the prediction. So first, we have for years, a certain number of years, 10 years, 15 years, it's flat, and then it goes up. So there is some feedback here, and clearly, here we have some problem in the response theory, because there is something interesting happening here on, guess what, on a decadal scale, that is a big problem. In a lot of problems happen there. Now, let's look at the meridional temperature gradient, and let's see the differences between north and south hemisphere. Look at the south hemisphere. The prediction is almost perfect, with a very, very small error. Look at the northern hemisphere. We have something going on there, and I have no idea what it is, but it's interesting. But I think it tells us about problems on the decadal scale. So the problem seems to be in the order of 10 to 30 years. Not below, not after. And looking at an even more weak observable, that is the temperature gradient north-south at 500 millibars. That's what we get. On the long term, we get, as we should expect, a decrease. For those who are experts in atmospheric dynamics, we expect a decrease of temperature gradient aloft. Look, the response is very non-trivial, but guess that the response theory gets the big feature. So a decrease and then an adjustment. And the same in the north and in the south. Of course, the more we start to look at observables, which are differences observable, we increase signal to noise. We increase noise to signal. So of course, we expect to have worse prediction, but I'm actually quite happy with what we get here. So concluding, I think so we can. I think a response theory is a very good way to look at problems of climate, and we can construct a lot of theoretical results we can use in very practical problems, and to do climate change prediction. I think we can assess the limits to the time scale we can predict, and we can formalize some problems we observe in modeling. And I think now I'm starting to work on the actual IPCC and climate prediction.net data, and I think one can prove that it's better to concentrate the computing resources in a slightly different way than usually done. Thank you.
Are there remarks or questions? Yes?
If I understand, what you propose is to kind of get more mileage out of model runs, right? So
Sorry?
what you propose is a method to get more mileage out of model runs. So you do one model run and then you can get results for other experiments.
I think you can reproject the yes.
And you avoid using models completely.
No, because you need to reconstruct. No, the models are a crucial element because you need to reconstruct the dynamics. Then, of course, what you look is that
just observing just from observational data.
Then you will. It depends how good your data will be and what will be your predictability skill you have. And the problem is that, attention, you have to set the forcing. So that is going to be important. And that is. So I'm not sure you can take out models. I think models are, a good way to ask questions at least. I think, Peter.
Colangeli?
Yeah.
There are many, but
okay. No, Valerio, I think that with your meteorological models, you may have the nice chance to assign to response higher order terms with some physical meaning.
Yes, that is what is missing, in fact. But the fact is this has been obtained with a very modest computer resources, and it's only 200 members of an ensemble. If we can do 10,000 members of an ensemble, we start to see, and we can, it's enough. This is CO2 doubling. We go to square 2 of CO2 because the problems are with a logarithmic scale in this case, and we can start to play the game of finding the difference between the first and second order response. You can reconstruct it in very simple algorithmic way, and you can look at, yes.
Yeah, thanks. That was fascinating. What wasn't clear to me is when you're reconstructing one model output from a previous one, are you essentially inferring the impulse response function from the first step change, or are you using the variability?
No, I'm using the step. I need the step,
right.
And then I use that to I convolute with a pattern of forcing that I have been given, that is 1% increase, and then I predict.
So you're not using the variability in the
No.
real trick here is you can somehow use the variability in the unperturbed state to get the sensitivity. Is that?
Yeah, but it's why do you want to do that? I mean, like in this case,
because we don't have a step function in the real world.
But we don't even have. But you should. But we have forcings. We have forcing, and but I mean, from the observation, it's a different sort of problem. This is if I want to reduce the complexity of the modeling as an exercise. This can help. I have to think about. This is a different problem. Maybe it's possible.
Glathard is the next.
Just a naive question. When you say that the SRB measure is robust with respect to noise, is this a sort of pathwise robustness, or is there some kind of mean sense in which?
No, in the sense that you find, so I mean, you know that if it's a SRB, it is the limit of for epsilon going to 0 of is Kolmogorov limit basically, and if you just plug noise into a deterministic dynamical system, you get the convergence, and it is the second order that matters, not the first order. It's a second order effect. So that is important. Then it's in this case depends on the kind of noise, but second, fourth, it's an even order. But you get the exact correction for any observable.
Who's next? I thought. No more? Thank you.